Now, my last video that I made was too long, and for the solar analysis, we really need to talk about where the errors come from, where the uncertainties come from, what is really behind this solar resource analysis. So in this video, I'm going to talk just about generally measuring yields and capacity factors. And then I'm going to talk about different ways to measure the amount of sunlight that touches a solar panel. And then when we get to performance ratios and all that, I don't want to get into too many details and get in trouble that I have gotten into, but why you might get different performance ratios and what kind of stuff you can expect and what kind of really questions you can ask for. Now, I really want to get into corporate PPAs. I've got a set of slides on the corporate PPAs, but the allocations that we do by period really could be important in these PPAs. Now, when I talk about the capacity factor and the yield. I know I've mentioned this in other videos. The capacity factor, whether it's a plane, what else? A conventional electricity plant, a horse, anything. It's you measure the maximum production you could get in an instant, whether it's the number of seats if you fill up the plane, and you divide that by the average number of seats. And the average number of seats for a plane could be, imagine it's full, then the capacity factor for the plane ride would be 100%. But if the plane's on the ground for half the day, then the capacity factor is 50%. That's kind of like solar. The yield is you sum up all the amount over all of the hours and then divide it by the maximum and you get the yield. Now, when you do that, you got to remember this STC, standard testing condition business, and the maximum is an arbitrary amount. If you have a Maserati and you push your pedal down all the way, you can figure out the fastest it can go. You can figure out the maximum speed, maximum miles or kilometers. For a dispatchable plant, you can take that knob and turn it all the way up and get the maximum. For solar, it's much more of an arbitrary kind of a number. It comes from our testing condition, and I think I've already talked about this. Okay, now we've talked about some of these equations and the capacity factor, and I'm going too much. Now, when we do this, remember there's somebody upstairs. Whether you believe in the Big Bang Theory and that's how the planets were created from the solar system, or whether you believe in you're more religious and think somebody upstairs causes the solar power with the clouds, somebody else other than you controls the amount of power that hits the plane, which I call in-plane radiation. And whenever you look at one of these resource studies, they start with the kilowatt hours per meter squared of how much hits the panel. And then there's somebody else who determines how much nighttime and daytime and clouds and all that stuff you have, and that how much you get from that person upstairs depends on how you tilt or track or put tracking on your solar panels. That's all that we can call that in-plane radiation, like I've already mentioned. And then you can put different kind of panels that have different sensitivity to the temperature. You can put different inverter sizes in. You can have losses from the wires, and I've said this over and over again, but that's all stuff you can control. And the performance ratio, whenever you do this, it's the output's going to go down generally, with perhaps the exception of a bifacial panel. And you're going to get less output because of dirt on the panels, because of temperatures reducing the output, because you make your inverters a different size, because the wires have losses, and all of those things that cause that output. You divide the final output by the amount you could get if you didn't have the losses and you just had the man upstairs or woman upstairs telling you about the solar power. That's the performance ratio. Now, when we talk about these resources, maybe it's good to talk about global irradiation. Now, when I said in-plane radiation, you could call that effective irradiance on the collectors. Oh, that sounds fancier. And then there's some corrections for reflection and soiling, which can be part of this. And finally, the energy injected to the grid is what's after the performance ratio. Okay, and then I have some general stuff. The first time I looked at solar power, I got so freaked out. I read a book and it talked about latitude and longitude and how you can, if you know how this Earth is going around the sun, I think that's the way it works, then you can kind of figure out the angles and get it. This is the standard testing condition. I've talked about it too much. Then we can have different kind of measures of radiation. This is the in-plane radiation, or that effective irradiance on collectors. I forgot to say that word properly, and this kind of illustrates it. This is on a horizontal plane. This is if it changes, and this is if you have tracking. And if you have tracking, depending on where you are, and the most extreme case I see for this is South Africa. For some reason, at least when you just put the numbers in the computer, the amount you get in addition for tracking in South Africa is dramatic. And that seems to be the case because I've looked at other studies. And then this is the amount you might lose for irradiation. And then this just goes through some issues with the performance ratio. And oh my God, I can't read that. And this is, again, how you might compute efficiency of a solar panel. You see how much radiation hits the panel, and you might get 15 or 20% out of it. But if you put more panels in, you get more sunlight. And if the cost is the cost per the amount of electricity you get out, not in, the efficiency, it's not like other things. The efficiency only affects the area. Now, when I don't want to promise this, but I really should make a thing about wind. This variation in the sunlight with insolation, of course, they call it something else here, to get to the, well, this depends. If it's really hot, you get less. If it's cool, you get more. And if it's dirty, you get less. And so there can be variations, that's for sure. And now we'll talk about the inverters and why you don't put inverter in. And that was just a little bit about the thing. I repeated that. Okay, enough. When we look at the performance ratio, what's causing lower amount to go to the grid, a big deal will be the temperature. Okay, and that one I expressed way too much. And then what we're going to do is we're going to look at some PV cyst and some other softwares. And here's the effective irradiation on the collectors. And then they adjust this. But this is the one they used. And what you can do is take this number. Remember, you could take this number, divide by 8,760, divided by 1,000, multiply by 1,000, and then you get the capacity factor. That's one way to do it. This is the capacity factor if there was nothing, if it was just purely the radiation, irradiance on the collectors. And then you got the injected to the grid. And when we have a capacity factor, you have the capacity, you have the amount in megawatt hours. You take this megawatt hours and you divide it by 8760, and you get the final capacity factor, and then the performance ratio is this divided by this. You could do it with a yield or the capacity factor. It doesn't really matter, but that's the kind of thing you want to look for. And when you look for this, and this is another output from the PV sys that I don't know how they do it. They had some very good guy kind of making a program, and the is it this one 1913? Here's the 1913. They start with the global horizontal radiation, and then they kind of go all the way down to the 2244, which is not it's this one, which is not exactly the one they use for the performance ratio. Okay, but they look at what if we take the horizontal radiation, we get 23.4% more for because we put it on a this in this case. I think I'm pretty sure they had the tracking. Okay, and even if it wasn't tracked, if it was tilted on the right way, you get more. And then they start subtracting, and the nice thing is they say, what's the biggest thing that matters? And unless you're in a cold weather place, the biggest thing is almost always this temperature. So here's my thought on this. Number one, look at this. And number two, if you get a report like this, and if it's in a really hot place and there's not much of a decline here, you start to question this. And when you look at the temperature coefficient, the biggest thing probably everybody's going to have a little losses. Some people might have a little more soiling than others, I know. And in the ratio, the amount the sizing of the inverter might be a little different, but it's really the temperature coefficient. So when you see different performance ratios, at least you can ask questions. So here are a couple of other examples. What I do is just collect the PV sys reports, and it's always this temperature loss. I was trying to make my waterfall graphs, okay, and show it what it is, okay, and this is different ways to express the performance ratio. And here's kind of some of the stuff in the Middle East, where I think it's pretty odd. We have, in this case, we had a smaller temperature effect than others. Now that might be because they have invented some kind of special panels, and they're using some different kind of panels that are thin film perhaps, or something like that. But it might be just because the consultants put a little factor in, and that's really, really what I want to get to throughout of this. Okay, and then that was a repeat. So what I sometimes do is just, if you have in these reports, that's why I put it, you have different temperature. Now this ambient temperature is not relevant for anything. It could be the temperature at night. Who cares? And it could be the temperature outside, but it's a temperature that strikes the panels that really determines the amount of losses you get. But you should see, when you see this performance ratio somewhere, it's not shown here. Okay, the performance ratio here. This performance ratio, which again, remember we could do it with the capacity factors month by month, or so I put the days in, the hours, or for the year. And you should see, when it's higher temperature, you should see a lower amount. And that's what these graphs show. And I've done this for different places. And that seems to be consistent. And then this is an example of somebody saying, no, we use these special different panels, and some panels seem to have a better record of temperature. So here, this temperature coefficient measures the percent change in the output relative to the percent change in the temperature. So if the temperature goes up, the output goes down, it's going to be a negative number. And these are the claims, at least. And what you'd really want to do is get somebody to guarantee this. You'd have to say, okay, I got to measure that temperature right on the panel. How are you going to do that? It's tricky. Maybe you can. I'm going to take that temperature on the panel, or maybe you take the panel out and take it to a testing place like that picture I showed. I'm not going to go back up. And then if we have polysilicon panels, they have a worse effect. So the higher the temperature, this is arguing for thin film. But then thin film takes more space, it costs more, blah, blah, blah. Maybe you can get some in China, and that'll be okay. Okay, so you can go through and look at these adjustments. And I'm what I try to do is go backwards and figure out the implied temperature coefficient. And then now what I'm doing, what we're going to do is get a little bit more into the uncertainties. And I took this people I worked with, and they oh Jesus, here's what they did. This is for a 200 million USD project or something. They didn't want to pay for PV cyst, so they got this one and they put 1 megawatt in, and they said, here's our performance ratio that plops out of this, and let's go to the bank. And they implied the performance ratio was 93. You could take this production for 1 megawatt and go backwards and figure out the implied what do we call this? In-plane radiation, insulation on the what was the damn word? Oh shit! I can't go back. All this crap here. What was this word? Here. Come on. Okay, I'm gonna get it. I'm sorry. I really have to get it. Okay, it was this one. Effective irradiation on the collectors. That's the word I gotta use. You gotta use fancy words so that you can look smart. Now, if you get a PV cyst, so we took the same thing and ran and got a consultant to really look at it. Then the first thing they did is they gave us a ratio, and they said out of the DC power, the ratio of the amount of power that we could theoretically get in direct current from our irradiation is 304, but we're only going to put inverters here, and this is a little small, I'm sorry, but then you can see how many inverters you put on and all of that. We're going to put 294 inverters, so the ratio, maybe I really want to do the ratio the other way. 344 divided by 295. Was it 295? 16%. 294. Okay, I'm not going to go through. And then we get, in this case, they gave a much higher performance ratio. And these consultants looked at the bifacial, and there was an increase in the yield from the bifacial. The global, and they show you the global horizontal radiation, and then they show you how much the increase in yield was from putting tracking in. And so that's the PV cyst. And then I went to the EU website, which I love so much. And in this case, the global, I just put a global. I clicked on the global one here. Remember, you can get that from my website, or you press PVGIS EU or something like that, and you get it. This one didn't have the global horizontal irradiation, at least not in this page. In this one, they gave it to us, and it was 1887, and this is 187. Oh, that was really similar. The difference occurred when we put in the tracking. In this case, the tracking gave you remember, it was on the correct collectors. It was the effective irradiance on the collectors, and they call it in-plane radiation. That's why I use this one, 2793. In this case, they have the 2403. So you're starting to get differences. The reason I'm telling you about these differences is, number one, as a finance person or investor or a banker, you can start to ask questions, and don't be afraid to say, I went to the website and I got this one. Why did you get this one? Let's go back and ask our consultant some questions and realize we have some other uncertainties going on here. And then we went to PV Watts, which is kind of the US version of the EU, but it doesn't have the fancy graph. You can't get the hour, you can't get anything. They gave a total irradiation of 2018, which is, different than these ones, okay? And I can't remember if that was a tilt or not. And they gave a performance ratio of 74%. Now the PVGIS gave 78%, and the consultant with the forecast gave 87%. Enough to start asking questions, isn't it? And then you can finally go to the World Bank, and they gave you the global thing, and the global always seemed to be the same, similar, but the other ones were different. So now let's get into P50, P99, and all that stuff. God, can you imagine? I'm making a video, and I haven't touched Excel yet. What in the heck's the matter with me? Now, I want to go through, when we discuss this, understand how you could incorporate some of these uncertainty characteristics in the analysis. And remember, from the last video, the difference in the uncertainty estimate drives the P50 versus P90, and how'd you get these differences? I hope that I've shown you this. Now, some of the uncertainty could come from just the measurement of the global horizontal radiation. Okay, good. And here's an example of this. I think this is a better example. This scale doesn't go down. I wish they would put this down to 0. And you can see these are different models. They're different models. And if you, what I did in the last one, I should kind of put this. Some of these used something called, I'm not going to try to pronounce that. And some of them, I don't know, they used a different source. I guess they came up with, I don't really know what that is, United States. They came up with different answers. Okay. But the key point here is that different sources, and what happened here to our NASA one is kind of bizarre. We could get uncertainty related to the first thing. And then the next thing you can do, maybe forest fires will affect the amount of radiation you measure per year. Maybe, I don't know, different lengths of the rainy seasons, things like that will affect the variation in year to year. Now, I have put here, need to make it larger. This is the standard deviation divided by the mean for different places. And I wish I would remember where I got that from, and I can't. So I'm going to go to the next slide. And this is where somebody tried to explain what P50 and P90 is. Basically, what's this one? P90, 10% chance that it could be below. So now I'll finally get to a little bit of Excel. If you, let's go to our solar uncertainty page. Okay, and in our solar uncertainty page, let's say right now they gave a P50 and a P75 and a P90, and what they did, we'll look at this a little more, is they gave this time they called it variability. Why in the heck is standard deviation that hard of a term? Couldn't you at least not do it in brackets? Doesn't every fourth grader know what a standard deviation is? I think they should teach it then. Please, I bet they do in South Korea. If you put equal normal distribution, what that does is it gives you this a probability. Okay, I've never kind of tried it like this, but and there's a way. Oh God, I did this with my friend Patrick, where you put a different standard deviation in and push this graph up and down. But what we do is we put in some value and then we get the probability. Okay, and when you do that in Excel, you just put the equal normal distribution and then you put in what value you're looking for. So let's look for a P90 case. And then this is the famous thing about Gauss and the standard deviation. He said he found this normal distribution, this shape, did the math on it, and was so much smarter and all that. And then you put a 1, and it's looking for the standard deviation. Whoops, it looks for the mean first, and the mean is always the P50 case, and then you put the standard deviation. And then you can put in 1, and that's the 10%. That's this P90. So that if you just put equal normal distribution, that's what you get. But if you go, so all we really need is this and this. You don't need anything else. And then you have to figure out how you got this one. That's my theme here. Okay, now, then after we do that, we can go backwards. We could put up here, let's put the P75. I don't know why you'd want P75. It's not a normal kind of thing. You put 0.25 and you go the other way and you put norm inverse. And that's what I had in NORM. And you put the norm inverse and it goes backwards. And it's actually easier because you just put in the probability, you put in the P50, and you put in the standard deviation. And that's all you need is that standard deviation. Okay, it gives you 811. They were rounding it off, and whatever. I can't put the other thing in because I'm on here. So I think that's what I was meaning to do here. If we wanted a P99, it's not on here. You just put norm inverse, and then you just go up to the probability, and you put in the mean, and you put in the standard deviation, and you get the P99, and then you can see what's the P99 relative to the P50. And it's about 85, and that seems to be a number. And my supposition, which could be completely wrong, is that people tend to put these standard deviations in to get something like this, or everybody puts about a same sort of standard deviation as a percentage of the mean in. Okay? But I just want you to think about things. Now, if you're lucky enough to be a banker and you collect actual data and compare the actual to the forecast, then you can really that's almost like that's almost a better way to do it. Simply look at 30 different studies and say, here's the prediction from the study, the P50. Here's what actually happened, and get a standard deviation from the actuals, and just actually kind of get it. Now, then let's keep going. So that's the norm inverse. And then I've got some other examples here where we get some differences. Here is a point I wanted to make, is that when we look at the actual variation from year to year, that's often very, very small. And if you go to the website here and do what am I going to do? PVGIS EU, that's the one I tend to get. And then the nice thing is they allow you to really look at some variations. And when you do this, you go to the solar radiation tool, and here's what I just want to show you. If let's just pick someplace right here. Let's make it. I bet you this is a good one. And let's just get the solar, the horizontal variation. And then if you look at the monthly data, they give you kind of a month by month. Let's see how good this place is. If we go to grid connected, let's see if we got kind of, whoops, how much. Okay, there's not much variation, and we get 2,300. I think that's very good. I have to almost put it into a capacity factor, and then you can say, oh, well, no, let's put the tracking PV in and see if we can do this. And then we get a lot more, 23 versus this, and it's all stable and all the rest of it. But then we go to the monthly data, and on the monthly data, you can put in different years and get this. And this time, instead of just looking at this, it doesn't give you the numbers. And then we go to this one, and we I'll leave it in this folder. And then we open that, and then you go over here, and you get the data, and you throw it into your Excel file, and you paste special as Unicode text, and you get one of these things. Then you go to my website, and you go to chapter number 1, and you go to the Excel utilities, and you get, or it's on the first page of this, and I get my read PDF to Excel program that people don't seem to like very much, but on this one I think it really helps. And you press Shift Control A, and you just press the second one and the green column, and what happens is it just will array it for you. Okay, and let's put our months in. So let's copy and paste special as transpose and get rid of all this stuff. Okay, and it was painful for me to write little codes because I kept on getting it wrong. For me, it's just good enough for now. Let's put a total here. And when we put a total, we can then do one thing with the standard deviation. And we can go downstairs and put equal average, and we get the average across years. Now, you should do it across the years. If you'd make a little graph of this, alternate and F1, and then you don't, please, I don't know. I read some book on graphs once, and they said, don't cut off the scale like that, you know. And then you can see there's really little variation. And so we can put the average and then the standard deviation. You see, I couldn't stop with the XL equal ST. I really was wondering if I would stop, if I would, and I would use the sample standard deviation, and then you can see what the average to this is, and it's only one, in this case, it's only 1.44. And that's the percent, but that doesn't count. Remember, when we looked at that resource analysis, you saw all those potential errors, all those other errors that could be made, and that's what we want to do and put in our analysis. We want to put everything together. So to put everything together, I'll leave this, why not? We can then, where's the solar uncertainty? And I did this here, so I'm going to take it out. They said, in this case, they put different kinds of variations in here. And this, for me, is we're finally getting really to the key. And for me, the key is that how much of this P50 and P90 stuff is really objective, or how much, excuse my language, is just a bunch of bullshit. Okay? This case, remember they had 3%, 4%. We better copy this and put this into our Excel file. Okay? So let's just see how they at least do it. Now, so in that case, let's put it down here. And make it a little smaller. And we have our 3% and our 2.4%. Whoops. And our 4.3%. I hope nobody thinks I'm drunk right now, like that other comment I got. And then they have 5.8 as the total uncertainty. How did they get that? Well, here's what they did. They squared it. Maybe you should ask them. Maybe one of the reasons I think you should maybe do this is you can show how smart you are. When you review, somebody says, okay, here's what I did. I took your pieces, I squared it, and then after I squared it, I took the square root. Okay, and then I get 5.77, 5.8. That's what they always do. That's called the mean square error. So if you can say, this is the solar resource uncertainty, that first one must be kind of like the thing we just did. Interannual climate variability. So they're somehow thinking they're smart enough to see how climate change might work. And then they throw in model uncertainty. I would want to see exactly what's behind that. That's this whole business of looking at how wrong you've been in the past. It would be really interesting. If that model uncertainty has been 10%, then you can put it in. Oh, interesting. If it's 20%, you get the number. And I would really want to see the historic errors in the model to get that number rather than just have it appear. And we can do the same thing here. In this case, they have PV module parameters. Oh, God, what bullshit. In inverter efficiency uncertainty. Let me see some historic record. Soiling mismatch. And then degradation, which is the big one, which shouldn't even be there. And then they get 6% variation. So just again, what they do here is they square it. And then after they square it, they go down and sum it. Let's put the sum up here. And this time I didn't even get it to work absolutely perfectly, I think. And did I take the 3%? I think that they took year by year variability, specified deviation. We need to understand everything about that. And then you take the square root of that. Okay, and I get 6.47. Good. That's what that mean square error is. Now, when I did this, of course, I was skeptical. I thought, oh, does this really work? So I went I went and made a simulation. This is a Monte Carlo simulation where I took, this was for a wind project. They gave the standard deviation and gave it as a percent, and I took the square of this one and then got the mean squared error of this. And then I said, okay, well, let's say they're all, let's go and put a random number and a different random number in for each one of these things. And then take this random number and use our normal inverse function and just assume we're just looking at the standard deviation. So I put 0 for the mean. And we get that for all of the components. These are like all those components. And then we get to the end, and then we sum this thing here, and then we just run it for thousands of times. Now this time, when and then I took the standard deviation of the sum. If I would have taken the standard deviation of the other stuff, and you can look at the code, and all that stuff, then you should get similar. Whoops. This, you get the standard deviation up here, you get the standard deviation up here, it gives you kind of the individual standard deviations when you just take a bunch of this stuff, and then you no, let's put this, shit, okay, let's put this down here, and then you do, what you do is you add up all of the standard deviations, not with mean squared error or anything else. And then you just have proven, when I do this for more simulations, it always kind of hits the mean squared error. When you add up all the standard deviations, okay, and then just because of randomness, one offsets the other, and that's why you need the mean squared error. So you can see this one was about right, this one was about right. And then when you sum all of this and do your simulations on each one of them, it proves that the mean squared error really does work. And I wouldn't even burden people in my class on this. Even what I told you might be a little bit too much. And here's really the final theme. Maybe that's, I showed you a little bit about the mean squared error, but this is this famous chart. I love this chart so much. It shows, it's all black, so you can't see, but we've got a P50. There was a transmission problem. This was a breeze to some kind of project. Here, obviously, is the P50, the top one. The P90 is obviously below the P50. I should say obviously. And the actual is up and down, up and down, and up and down. And here, starting out, we're doing really crappy because we're at P90. That's supposed to happen 1 out of every 10 years. And we go to this year, we're not. Here's the P90. We're way, way below the P90 because we didn't have any accounting for the uncertainty related to the transmission being available, and we didn't make our downside case correctly. That's where it comes in, and the consultants put all their little statistical factors in, and you got some rubbish. And So I am going to stop the video right here and just urge you to understand that it's just a downside case, and it can account for all these problems you have with the resource studies, and it's important because it affects the debt size, and that's enough. Bye.